This lecture is going to be on reaction rates. So let's go ahead and give ourselves a title. A rate is any sort of change in a quantity per unit time. And so, of course, in chemistry, we're going to be talking about change in concentration in terms of molarity. And so, in kinetics, the units are going to be usually molarity per second. Okay, so that's the first thing I want to emphasize is that reaction rates do have units on them. It's very important when we start working with some of the math equations. Okay, so let's just draw a picture for a particular chemical reaction. I'm going to use an example of nitrogen dioxide decomposing to nitrogen monoxide and oxygen. Okay, so we're going to start this experiment with more or less 3 different time periods. I'm going to go 10 seconds, 20 seconds, and 0 seconds. And we're going to measure the molarity of NO2. And so we're just going to say that's 1.00. And NO, instead of just starting at 0, which we would normally do a reaction, let's just go ahead and assume there's already some nitric monoxide and molecular oxygen. So we're going to put 0.100 and 0.200. These are all molarities, okay? So we're going to start with these initial conditions. We're going to run the chemical reaction and see what happens at 10 seconds. Well, at 10 seconds, the molarity, for example, may drop to 0.964. And this actually has to increase by an amount proportional to the amount of NO2 that has gone away. So NO2 has decreased by 0.036, so this must go up by 0.036. So I know that that's what it's going to be if it's just a simple reaction. Now molecular oxygen goes up at half the rate, and so if this is going up 0.036, this must go 0.018. So this is 0.218. Then later on, at 20 seconds, we're going to look at the quantity 0.934, 166, and 0.233. All right. So the rate is the slope of this graph. So let's go ahead and plot these concentrations, what they would look like. Okay, so NO2 is going to look like this and this and this. So this will be at 20 seconds and 10 seconds and 0 seconds. So if this axis is time, this axis is going to be molarity, and so the pink dots will be NO2. Now, it doesn't look like it's changing much because it's actually going down quite slowly. Let's go ahead and use a different color for NO. It's going to start out at about 0.1 and go up probably about the, well, it's actually going to be going up exactly the same rate at which this is decreasing because the change in NO2 is stoichiometrically related to the change in NO. Now, molecular oxygen, which is going to be starting at 0.2, is going to be done in orange. All right, and it's actually going to be going up at a slower rate because there's only 1 oxygen appearing for every 2 nitrogen monoxides appearing and then every 2 of these disappearing. Okay, so let's draw another plot of what this would look like at very long times. The NO2 would be going down the NO would be going up, and the molecular oxygen would be going up as well, but to some limiting value. And so we can actually figure out what it should be at infinity if the reaction goes to completion. 1 should go down to 0. If this goes down by 1 molar, this must go up by plus 1 molar, so that's 1.10 molar. And if this goes down by 1 molar, this must go up by 0.5 molar, 0.700. All right, so that's kind of what I tried to draw here. So this should be 0.700, 1.1, and the last one should be 0. All right, so now what we're going to learn is actually how to calculate a rate. And so the rate is the slope of these graphs. So we need to calculate the slope. Rate is the slope, and the way you calculate slope is rise over run. Okay, so we're going to do the rise over the run for NO2. So from 0 to 10 seconds, and this is called an average rate. Because it's continuously changing, and you can see actually, as you would expect in most chemical reactions, it'll be fast at the beginning, and then get slow and eventually reach 0 as you start to run out of reactant. So the average rate of change. So remember, chemical reactions describe changes. They don't describe how much NO2, how much NO, how much O2. These numbers had nothing to do with these numbers. I just picked them at random. So it's average rate of change in NO2 from 0 to 10 seconds. So the rise is going to be 1.00 minus 0.964. And then the change in the time is 0 minus 10. And that's molars. That's going to be seconds. And so the answer we get is going to be minus minus 0.036 molar per second. Okay, let's go ahead. Now that's just from 0 to 10 seconds. Let's go ahead and calculate the change in NO. So we're going to do everything exactly the same except NO. And NO is going to be 0.036 for the rise, except now it's going up. So it's 0.036 divided by 0 minus 10. So it depends on which way we do it, but we're going to get plus 0.0036 molar per second. Okay, so the change is related by stoichiometry. And since the rate is related to the change in the numerator and the change in the time is the same for every component in this reaction, then the changes, the rates of change are related by stoichiometry. One last one to do is oxygen. And that's going to be plus 0.0018 molar per second. Okay, so now we actually have 3 different rates of change, even over the same time interval. So we have to ask ourselves, what one of these are we going to call the rate of reaction? Well, the way we define rate of reaction is to take any one of these, and if it's a reactant, we expect it to be going down, so it'll have a negative slope. If it's a product, it's being made, so it's going to have a positive slope. So the first thing we want to do is define the rate of reaction to be a positive number. So it's probably best to just go ahead and pick one of the products. So we'll have a positive number. Then the other thing is, this will be twice as large a change as that, and we can see that indeed occurs. And so what we do is we divide by the stoichiometric coefficient. So if we take this number and divide it by 2, or this number and divide by 1, we get the same answer. So the average rate of reaction is plus 0.0018 molar per second. Okay. Now let's go ahead and calculate the average rates of change for NO2 and O and O2. You can go ahead and do that yourself. And then calculate the average rate of reaction for the interval from 0 to 20 seconds, and you should get the average rate of reactions 0.0015 molar per second.